Hello everyone. Let us today discuss the Fourier transform in continuous and discrete domain. We will do the Matlab coding also in this lecture. If we start with the mathematical characterization of the sampling operation and define an impulse train function, it will be defined as st equal to sigma n going from minus infinity to infinity delta function of t minus n capital T sub s. Now this is the impulse train. If you put the value of n to be 0, you get delta t, so that will be represented by this pulse at this 0 or at the origin. If you put n equal to 1, that will be this pulse. If you put n equal to minus 1, that will correspond to this pulse. So for various values of n, you will get impulses. So that means it is an impulse train. And if you sum up all the pulses, that will be your impulse train function, which is st. All right. Impulse train signal or function also has Fourier series representation, which can be written as. Now, st can be written in terms of Fourier series by sigma k going from minus infinity to infinity sk e to the power j k 2 pi by capital T sub s t, where sk are the Fourier series coefficients and which are calculated using this formula. This is equal to sk will be calculated as 1 over ts integral going from minus ts by 2 to ts by 2 st e to the power minus jk 2 pi by ts t dt. All right. Our st is a delta function, so we place at the position of st the delta function delta t, and if we solve this integral, we will get it equal to 1 over capital T sub s. All right, and we need to substitute the sk value in this expression. Then we get the impulse train function as 1 over ts sigma k going from minus infinity to infinity e to the power j k 2 pi by ts t. Now, if we use the property of the Fourier transform Fourier transform of the exponential function as e to the power j omega naught t, if we take the Fourier transform of this exponential, we will get it equal to 2 pi delta omega minus omega naught. Now, this is our exponential function, and if we use this property, we can get the Fourier transform of this impulse train function, and we can get it equal to 2 pi. We use this formula 2 pi by ts k going from minus infinity to infinity. So this delta omega minus, now what is the value of omega naught in this property? Uh, the omega naught in this property will be equal to, in our expression, and it will be equal to k omega s, right? This is k is also there, omega s, which is equal to 2 pi by ts. So our, if you make the right substitution, you will find that s omega will be equal to this expression, which is the Fourier transform of the impulse train function. Now, so we what we have done is we have defined the impulse train function, right? We have taken the Fourier transform of the impulse train function. Now let us see what the sampling operation, if put analytically, what is the sampling operation? Now sampling operation is basically the multiplication of this continuous signal and impulse train. Now if any continuous signal is given to us, for example in this diagram, the continuous signal given is a sine wave, right? Now sine wave, if we need to do the sampling of this continuous signal which is sine wave, we need to multiply this signal with impulse train function, right? You multiply the two, the continuous signal and the impulse train, you get the product signal, and the product signal will be this sampled signal, right, which is the multiplication of the continuous signal and the impulse train. Now we know that the product signal is given by this multiplication. and if we put the value of st which we defined in the previous slide, we will get is xst equal to continuous signal into this function, which is the impulse train function. Now let us look at this property. This property is that if a function is multiplied with delta t minus t0, then what will happen is t0 will t will be replaced with t0, and we get it equal to ft0 delta t minus t0. Now in this case, xct is the function which is ft, and delta t is this value. Xct is the function. Xct is to be replaced with xct0. What is t0 in our case? T0 is nts. If you compare these two expressions, you will see that what is t0? T0 is n capital Ts. So xc, so our ft0 will be xc nts and delta t minus nts. All right, because t0 will be equal to n capital T sub s. And we can also express this x sub c nts by xn also. So our product signal can be represented with xn delta t minus nts sigma n going from minus infinity to infinity. This is our product signal, the sampled signal basically. All right, now let us look at the Fourier transform of the continuous time signal. So we know that the Fourier transform of the continuous signal is given by this. We need to we need to calculate the Fourier transform using the using Matlab. Right. Now, to start with, we will draw the graph of the cosine signal first with period 1 by 2 on, and the time interval is given from 0 to t, 0 to 2, and we need to calculate the Fourier transform of the cosine signal using Matlab. We will first define a time vector with steps going from time vector going from 0 to 2 with steps of 0.001. All right, so this is my time vector. Since the period given is 1 by 2, so that means the frequency is equal to 2, and I will define the analog signal, which is defined as cos of 2 pi ft. All right, so again, this is the time vector, frequency defined. This is the signal, cosine signal defined. Now we can plot the continuous signal by plot function like this. We can label x and y axis, and we can give the title to the graph. If we run the program on Matlab, we will see that this is the sine wave generated. All right. Then the Fourier, we know that the Fourier transform is given by this formula. Now we need to we define the frequency interval. First, we define the frequency interval on which the Fourier transform is to be calculated. The frequency interval over which the frequency Fourier transform is calculated is chosen as minus 8 pi to 8 pi. So this is the interval chosen where we will calculate the Fourier transform, right? Which in Matlab, which is created using the line space command. So up till here we will plot the continuous function. We define it. We define a variable w or omega. Line space, it is w, you can take it as w is equal to line space minus 8 pi to 8 pi, because this is the interval we have chosen for calculation, minus 8 pi to 8 pi, and in between, and that will go to that will take the steps as length. That means that because our t vector is coming from here, so the length of this t vector will be the steps from minus 8 pi to 8 pi. So that is defined by this length space function in Matlab, which is the values will be equal to w. Now, so this is the usage of the length space, and now we will put a for loop where the w will run from, where the time intervals will run from 1 to the length of this w, which will come from this expression. All right, now because we need to calculate, if you see here, we need to calculate the, because this we need to calculate this integral, integral goes from minus infinity to infinity, but to limit this integral we have selected the interval from minus 8 pi to 8 pi. Actually we need to calculate this integral, all right, using Matlab. So this is the interval selected. The time intervals are, the step size for the time is selected uh, between minus 8 pi to 8 pi, right, with this time vector. Okay, so we put a for loop here. For loop will go from each time step, right? And inside the for loop will be this continuous function. Continuous function. That means the Fourier transform function of xct, and in the above integration can be achieved using the trapezoid MATLAB function. The integral x dt can be calculated using, so this is the format of the format of the integral calculation using the trapezoid function. Trapezoid function will calculate the integral with respect to t. Now this is the because this, if we put the, in our case if we define the Fourier transform as trapezoid, because the integral has to be calculated with respect to t, so first t will come and then the expression will come xct, because if you look at the expression, it is xct e to the power minus j omega t dt, so we have to put it here xct into exponent of minus j omega I, because these steps will come from here into t, right? And this for loop will actually calculate the values, and we will end the loop here, right? Because we have taken a variable here I also, so that means xcw will give us the table of values corresponding to each step. Now, so that is up to the end. Now if we want to plot the values, we generate, this is first figure generated, now we generate another figure and plot the absolute, the magnitude response of this Fourier transform. So we, because the um, in the magnitude response, the x-axis will have w, on the y-axis will have the absolute value of the magnitude of this expression, that is the magnitude response, and we plot and label the x-axis and y-axis, right? Two peaks will come. When we run this program, we get the Fourier transform of cos 2 pi ft. If we inspect this figure, we see that we have two impulses located at points minus 4 pi and plus 4 pi. And if we determine the time duration over the integration, we obtain better impulses at point 4 pi minus 4 pi to 4 plus 4 pi. That means if we increase the time steps, you can see that if you change the code, uh, earlier the time range was from 0 to 2, now we go from 0 to 20, and with a step of 0.001, if we run this program, right, so you will get better peaks at 2 points, right, minus 4 pi and 4 pi. These will be the peaks. Okay. uh, what is along x-axis is omega, which is equal to 2 pi f. So you can get the values from here. What is f is 2 pi f. So 2 into pi into frequency is 2. So you will get around 12.5 here, minus 12.5 here, and 12.5 here. All right. So these are the two, because the frequency is 2 selected. Now, if you further increase the time scale from 0 to 40, you will see that you will get even finer peaks representing the frequency of the in their frequency in the Fourier transform of the cosine signal. So that's how you can take the, you can calculate the Fourier transform of the cosine signal for the continuous time signal. Now, let us look at the Fourier transform of a discrete signal, where the, now if we understand, we know that the, if there is a continuous signal given, and how to discretize the signal, you need to replace t with n capital T sub s, where capital T sub s is the sampling period. right? And the Fourier transform of xn is given by xn e to the power minus j 2 pi n ts, where under sigma, where n goes from minus infinity to infinity. Okay. Now, if this is the Fourier transform of the discrete signal xn, uh, we can also express the Fourier transform in terms of a continuous signal. We have already seen that. Yeah, and it is given by 1 over capital T sub s, sigma k going from minus infinity to infinity, x sub c w minus k w s. Now, if we equate the right hand side of both the equations, what we get is this equation sigma n going from minus infinity to infinity, xn e to the power minus j w n ts equal to 1 over, we will bring this term here, 1 over ts k going from minus infinity to infinity, and this xn xe value. Now, if we equate, if we say that this whole term, because if you see uh, uh, this W, if we take the variable as the WTS here, and we represent the whole term as xn WTS, then this side will yield what we call we see that this will be 1 over ts. Now if this term is x and wts, then this term is put as it is. Okay, now from here uh, we can obtain this x and w by replacing w with w by ts. Now here we what we will do in this expression is we will replace this w with w by ts on both sides. Now if we replace this w with w by ts, ts will cancel out, so it will be x and w. And here also we will replace this w with w by capital T sub s, and this ws will come as it is, so we will get this expression. All right. Then if this is the expression that we have got, which is x and w equal to 1 over ts, that means the Fourier transform of the discrete signal is expressed in terms of the continuous signal, right? Now let this xw equal to 1 by ts xc w by ts. Now if we put this term here, what we get is what we will get is xcwts, we will get it equal to this term equal to xw minus k2 pi. All right. Now which says that the x and w, what is x and w? This is the Fourier transform of the discrete signal. Now this is a periodic signal with its period equal to 2 pi. This is very important result, that the Fourier transform of a discrete signal is a periodic signal with its period equal to 2 pi. Since x and w is the Fourier transform of a digital signal, it is periodic with 2 pi. All right. Now, if the digital signal is also periodic in time domain, then its Fourier transform is periodic with 2 pi consisting of pulses spaced by multiples of t, 2 pi. Same thing as I have already expressed. Now we need to get the Fourier transform of the discrete signal, right? And we need to write the Matlab code for that. Now, clearing everything, what we will do is we will create the time steps from within range from 0 to 2, and the step size taken is 0.001. And we know that we are in our example, in the previous slides also, we have taken the frequency of the signal as 2. The sampling period is chosen to be 1 over 16. We create a time vector from 0 to 2, and with steps of 1 by 16, which is the sampling instant. Now we can get the value of n. N will be equal to, this is the sample number, will be equal to ts by t, capital Ts, small ts by capital Ts. This is our continuous signal. We know how to define it. This is our discrete signal. We know how to define it, and we create a figure here. We create a subplot. We plot this continuous signal. We label and give the title. We create a subplot here, and we create using stem, because plot will create the continuous time signal, the stem will create the discrete signal. This is the x-axis variable, xn is the signal, r is the color, and this will represent the circles, the dots. X label, this is the labeling, this is how the labeling is done. Title is given. Now this is the length space, because we are selecting for the Fourier transform, we are selecting a range from -8 pi to 8 pi, as we did in the case of continuous time domain signal. Now we will create a for loop where I will go from 1 to the length of this w, which will come from this expression, and trap z will be used to generate the to get the integral part, and some will get the summation part for the discrete signal, and this will be for the continuous time signal. So both expression we will use for calculating the Fourier transform. Now we will create the another figure, another subplot. What we will do is we will plot the absolute the magnitude response of XCW. We did earlier also the same thing. We label the things, and here we do this plot with the x-axis variable as w, and we take the magnitude response of the discrete Fourier transform, right? And we label the signals here. So then we will see this is the continuous time signal, right? This is the sampled version of the same signal. We have already seen how to do this, and this is the Fourier transform of the continuous signal, and this is the Fourier transform of the digital signal. Now you see that Fourier transform of the digital signal will be repeating with a period of 2 pi. So the same signal, these two peaks are there, so these two peaks will come here, these two peaks will come here, these two peaks will come here. So this will repeat with a period of 2 pi. So that means the digital spectrum will repeat, will be periodic with a period of 2 pi, and this is the analog spectrum, I mean the Fourier transform of the continuous signal. All right. So this is how we can obtain the Fourier transform of a continuous time signal and a discrete time signal. With this, I finish my lecture. Thank you.